Hi, here we are discussed about the low power system for detections of symptomatic patterns in audio biological systems. In this paper, we are discussed about how to monitor the patient uh, based upon that audio biological signals. Okay, so once the patient conditions, we need to monitor at every second so that we are identify this paper to monitor the patient's symptoms of cough, sneeze, vomiting, this kind of things. Okay, so how can we are identify these things from the audio signals? Okay, that's a study of this paper. So we can use the mathematical calculations for quasi average metrics and the coefficients and Mel frequency spectrum based analysis. Okay, so this kind of things we are used, and we'll be design the code on VGGL, and we'll be simulate this on code on model sum and synthesis this code on Xilinx. Okay, so here I'll be show the diagram for figure 1. Okay, so here we are taken the input from the audio signals. It will be transferred to the Fourier transform and MEL filter based energy and log and discrete cosine transformer. So okay, so here the main important diagram is this one. Okay, figure 5. Here once I will be give the input signal to the discrete wavelet transform. The discrete wavelet transform, it will be differentiate 6 type of frequencies. That a frequency it will be given on here. Okay, so d1, d2, d3, d4, d5, d6. It will be range. It's called for band pass filter. Okay, so we can use for high pass and low pass filter through FAR or anything else. Okay, so the frequency it will be differ for d1, d2, d3, d4, d5. So based upon the signal range of frequencies, the output will be differentiated. Okay, so example, the d1 equal to 2.75 kilohertz and 13 d2 equal to 1375 hertz and d3 equal to 687 hertz. Okay, so where it will be given, so here they are given the various values of di are classified as the coefficient of interest for specific symptoms patterns. For instance, the acoustic patterns corresponding to wheezing, vomitings are resolved in D5 and D6. Okay, so the D5 and D6 based range of signals, it will be identified wheezing and vomiting. Okay, and the D4 and D5, it will be identified for burp and bleaching. Okay, the cough, it will be identified for D3. Okay, this kind of things we are identified easily through this 6 signals. Okay, d1 to d6. Okay, and the d6 is a last signal, so we are find out the energy for that signals. The energy is a same, it's nothing but the multiplier. We are boosting the signals, that is called energy parameters. Okay, so A, and B is a CL parameters. Okay, so CL means we are find out the different and calculate that accumulator based cost line values. And the figure C is for QA. Okay, quasi average. Okay, so this kind of things we are designed, and it will be passed into discrete cosine transform. The outputs, every outputs for energy, cost line, weighted quasi average and discrete cosine transform, it will become on detection threshold. So we can possible to detect the threshold values and identify the signals for vomiting, wheezing, bleaching, coughing, sneezing. Okay, so we have taken the samples, some samples here for audio biological systems. So bleach, burp, cough. Okay, so this kind of signals. So once I play these signals, yeah, just wait. Okay, this is the output. Okay, so once I play this signal, the sound for bleach, it will happening. Okay, uh, these are all the sounds in medical. That is it. It will be have for this kind of sounds. Will be take it. Okay, so how we are convert this signals, the sound signals to hex values. Okay, so that is the main work here. We can use MATLAB to convert these sound signals to hexadecimal values. So this is a GUI for the input is audio signals and raw data. Okay, this GUI, it will be helpful to convert audio signal to hexadecimal values and hexadecimal to audio signal values. Okay, so this audio signals I'll be entered here, the wave format, right? So wave and MP3 format, both it will be have. Yeah, just wait. Cough. Okay, the sound has been added into the systems. Okay, at the same time the hexadecimal value, it will be generated here. Okay, the input sound, the details that will be mentioned this here, right? So this signals, it will be generated. Okay, this is a hexadecimal values for that signals. Okay, so we are taken this type of signals from here for bleach 1, burp, cough. Okay, so we are read the signals based upon the file reading code here VHDL. Okay, so which signals we need to identify. Okay, so this signals we are given here, and will be written the code for top audio biological system. Okay, so the input is clock, reset, start, D audio input, bleach, burp, cough. Okay, so we are having only for three data set for this audio signals, so we are given this. Okay, so and we are written the code for DWT, energy, cost line, QA, mel filter, and DCT, direction thresholds. Okay, this kind of things. Okay, so the data audio input, it will be given to DWT and take the output for three samples of D1, D2, D3, D4, D5, D6. Okay, so what the DWT will be work means, it's the same, it's a filter. Okay, the filter coefficients, it will be taken from MATLAB for 2.75 kilohertz. Okay, this one, and this one for 86.25 hertz, and this one for 172 hertz, and this one for 343 hertz, and this one for 687 hertz. So based upon that table 1 in the paper, will be take that filters from DWT. Okay, so that's the output, it will be given here for data 1 to data 6. Okay, so based upon that architecture in the paper, so data 6 it will be boosted from energy, and the data 5 it will be boosted from cost line, and data 4 and 5 it will be boosted from QA, and mel filter it will be given for data 1 to data 6, and it will be find out the mel output. Okay, so mel filter, we are using this reference papers, uh, reference paper, the comparative study of the performance FPGA based mel filter bank and Bog filter bank. Okay, so this paper we are taken reference, the architecture of mel filter bank, it will be designed here. Okay, so mel filter. Okay, so and the energy, cost line, QA, so this kind of things it will be added. Okay, and we are similar to this code on VHDL. Okay, so now the file reading code, it will be have for the file input is burp. Okay, so this is a burp output. Okay, digital audio input, and this is a audio signal for burp. Okay, so we have find out this burp signal at the end of the file reading, the start will be goes low, so which signals it will be identified. So this one is a bleach or burp or cough. Okay, so which signals, so I'll be given here for burp. Okay, so the burp will be identified. Okay, so I'll be show the step-by-step signals. This is a DWT output. Okay, so this is an input, and step by step we are reducing the frequency, right? So that frequency it will be given here. So data 1 out, data 2, data 3, data 4, data 5, data 6. Okay, so at data 6 the frequency level, power level, it will be very less. Okay, so that's the things will be identified, what the symptoms it will be have. Okay, so cost line and QA and mel filter and direction thresholds. Direction thresholds. So the direction thresholds, it will be have some amplifications in energies. Okay, so we can easily find out the energy values to differentiate the signals, and will be find out the outputs based upon that threshold range. Okay, so the threshold range, it will be given on yeah, 2 minutes. Yeah, these things will be given the bleach, bug, cough, this kind of threshold range, it will be given here. Okay, and so once I change the signals in the file reading for to identify cough or bleach, I'll be given here bleach. Okay, and then I'll be go for transcript and model sum to sim.2. This is a running procedure. It takes some few minutes time to run the code. uh, if you enter the do sim.do after point out the directory, it will be automatically run. Okay, so this is the output for what, for bleach. Okay, so the signal will be differentiate. So birth and beach. Okay, this it will be identified for end of that start output. Okay, so this is the signal is beach. Okay, and once I'll be change this output to cough. uh, yeah, wait, cough. I'll be run this output to do some dot do. This is a cough based signal. So now the cough bit is 0. You can wait after the signal finished, and start bit, it will be goes low. Will be identify the output based upon the threshold. So we are calculating the threshold for, yeah, this cough, it will be high. Okay, so this is a simulation output we are find out here successfully. Okay, so and we will be synthesize this code on Xilinx vertex 5 SX 100T2FF1738, this based FPGA. Okay, so and we will be show the slices, registers, and flip-flops, how it will be taken. Okay, so I'll be show the RTL schematic for audio biological systems. So the data input, it will be given, and clock, reset, start, and bleach, bulb, cough. So instead of this RTL design, so will be shown the input. So this is a data input. Okay, so it will be given to DWT, and DWT will be find out 6 outputs. That output will be given to cost line, energy, QA, this kind of things, and DWT. So data imaginary and the data real, the two data it will be needed. So DCT, it will be taken. Okay, so and the DWT, it will be have for 6 type of filters, and mel filter. uh, yeah, I'll be shown the direction threshold. So the 2 minutes. Yeah. Okay, this is the overall schematic diagram. So DCT, so energy, QA. Okay, so this kind of things, and and this is a power report. For the power, it will be take for 2.066, and this is a area report for LUT size available and required. uh, okay, so flip flops, how much it will be take. Okay, so this kind of things is the output parameters. Okay, okay, thank you, bye.